Hello and welcome to Otten Math. In this edition of Otten Math, we're going to talk about infinite geometric series, and we're going to talk about some of the problems involved in figuring out sum of infinite geometric series. So as you recall, in the lesson portion, we highlighted three different possibilities between arithmetic and geometric series. First is when I have an arithmetic series, my constant difference gives me a sum which is continually increasing. So in this case I have 1 plus some value plus another value or the same value, and so on and so forth. And that value continues to increase or get larger, or in the instance where the constant difference is negative, my value becomes more and more negative. And either way, as I take the sum of the sequence, the sum of the terms in the sequence, I end up moving closer and closer to infinity, or to negative infinity. Now if I take a geometric sequence and I add the terms in those sequence, and I do that on into infinity, in the case where the ratio is greater than 1, or the absolute value of the ratio is greater than 1, my value of each term is increasing in value either positively or negatively. So in this case I have a ratio of 3, and so I have 3 to 1, 3 to 1, 3 to 1, 3 to 1. My values continue to increase. And as I move into infinity with the terms, my series also moves to infinity or negative infinity. However, in the case of the geometric sequence where the subsequent terms are less than the preceding terms, where the constant ratio, the absolute value of the constant ratio, is less than 1, then as I move into infinity, adding the subsequent terms, or an infinite number of terms in the sequence, and that series approaches a finite number. And that finite number we can figure out using the formula that we've talked about. So in this case I have an a sub 1 value, my first value of 1, and my constant ratio of 1/2, whose absolute value is less than 1. I can figure out that the sum of all these values, as each of these values continues on into infinity, is going to be 2. So you recall that sum is going to be equal to the first term over 1 minus the constant ratio. So let's take a look at a couple of problems. First one is to find the sum of an infinite sequence where your a sub 1 value is 1 and your r value is 1/3. So you can see that this closely approximates the sequence rule which we have, which is that a sub n is equal to the first term times the common ratio to the n minus 1. So we talked about this rule before, and as I write this into summation notation, you can see that a sub 1 is reflected as 1, the constant ratio is 1/3. That's all taken to the I minus 1, similar to the n minus 1 as we have in the rule. So in this case we know that our a sub 1 value is 1, and our r value is 1/3. So as I plug the values into the rule, I can see that my sum of this infinite geometric series is going to be 1 over 2/3, or 3/2. In the next problem, we have a similar problem, but with different values. So we take our rule again, a sub 1, which in this case is going to be 1/4, because when I is equal to 1, 1 minus 1 is 0. 1/4 to the 0 is equal to 1, and 1/4 times 1 is equal to 1/4. So my first term is 1/4, and that's divided by 1 minus my common or constant ratio of 1/4. So I get 1/4 over 3/4, or 1/4 times 4/3, which is the same as 1/3. And that's the sum of the infinite geometric series whose value of a sub 1 is 1/4, and whose constant ratio is also 1/4. So now let's take a look at a different problem. In this case, I'm not given the values in summation notation. I'm given the a sub 1 value. I'm asked to figure out what the constant ratio is, and then to put it into the formula for the sum of infinite geometric series. So I can see my a sub 1 value is going to be 1/2. And I figure out what my constant ratio is by taking the one term and dividing it by the preceding term. So it'll be 1/4 divided by 1/2, which is equal to 1/4 times 2 over 1, which is equal to 1/2. So I have my R value of 1/2. I have a sub 1 as 1/2, so I can plug it into my formula. And again, the formula is the sum is equal to a sub 1 over 1 minus r. A sub 1 in this case is 1/2. 1 minus r, which is 1/2, is equal to 1/2 over 1/2, and so my answer is 1. Now we can apply what we know to repeating decimals to figure out what the value of a repeating decimal is as a fraction. In this case it says fraction, but as a fraction in lowest terms. So 0.1212121212 is the same as 0.12 times 0.01 to the n minus 1, right, plus 0.12 times 0.01 to the n minus 1, which in this case would be 1, plus 0.12 times 0.01 squared, and so on and so forth. So the first term, this would end up being 0. And we can see that we get 0.12 plus 0.0012 plus 0.000012, and so on and so forth. And we provide an equivalent expression to the repeating decimal that we've just outlined. So in this case, we have our sequence formula, where a sub 1 is equal to 0.12, and our constant ratio is 0.01. So plugging that into the formula for the sum of an infinite geometric series, I end up with a value of 0.12 over 0.99, which is the same as 12 over 99. And then reducing this, taking out a common factor of 3, I end up with 4 over 33 as my fraction, which in simplest terms represents my repeating decimal of 0.1212. So let's take one more example. I have 0.555, and that's the same as 0.5 times 0.1 to the n minus 1. So the first value of n is 0, 0.1 to the 0 is 1, 0.5 times 1 is 0.5, plus, when this value is 2, I have 0.1 to the 1, which is 0.1, times 0.5 is 0.05, and then 0.005. And so this value approximates the repeating decimal of 0.555. So my a sub 1 value is going to be 0.5. My r value is 0.1. And I end up with 0.5 over 0.9, or 5 over 9 as my answer.